water table. Right? That looks familiar? That was up there on Tuesday, right? The house is there. Right? It was on something like that. Was on the board before. Okay. So, the only place that water can get into that sandstone is up here. So this confined system has a very small, very limited recharge area. And unfortunately, we tend to do stupid things. We build shopping malls and parking lots and food processing plants and chemical warehouses on top of the recharge area. Yeah, that's not smart. And so this sandstone aquifer has a chance of going dry rather quickly and with a long time waiting for it to be filled. That water being confined, being trapped, is under great pressure. We scientists can measure how much pressure that water is under. And we can use mathematics to calculate how high that water will rise when the pressure is let go. And that's called a potentiometric surface. That is the height calculate that with mathematics. I can guarantee, almost guarantee, that most everyone in this room has already had some experience with this. And you just didn't know what you were doing at the time. You have to assume it's summer, and that really obnoxious kid from down the block is there. Who knows? Maybe back then, maybe it was you, right? And he's complaining. I want to drink from the garden hose. I want to drink from the garden hose. Okay. What are you doing with that garden hose? He's there at the other end. Where's the water? Right? And the longer you crimp that hose together, the more pressure is building. And the stronger, the higher, the faster that water's going to come flying out the other end of his nose. Right? You're holding it. You turn the water on. And it's backing up in the faucet and spraying all over the house. Just a little longer. You've either done that to someone or had it done to you. I used to fall for it every time. And then you let go. All over the place. That's a potentiometric surface. You're already know in your mind that the longer you build the pressure, the higher that water's going to come shooting out the other end when you let go. So you've done science and math you didn't even know. You do use math every day. So we can calculate that for a confined aquifer system. So that when we put a well in here, we drill our hole for the well, that hole drops the pressure. It's like jamming a Phillips screwdriver into a spray paint can. I don't recommend it. Okay. Use cheese whiz, it's easier to get off of you. Okay. So you drop the pressure, that water's going to come flying up there all on its own. And it'll come flying up the well, and it will rise to the height of that potentiometric surface. When the water has enough pressure to be able to do this, that's called an artesian well. And that is the only thing that the word artesian means. It means they didn't need a pump to get the water out of the well. It comes up out of its own pressure. It doesn't mean that it's any good for you, or that it's any better for you, or that it's any more pure, or any more clean. It just means they didn't waste electricity on the pump. So don't be suckered in buying some $8 bottle of gourmet water because, you know, it's artesian. That's all it means. Now, this well will only continue to be an artesian well as long as that sandstone remains full. If too many people get into the system and start using that water table is going to start to drop. And if as the water table lowers, you'll lose that pressure, and you'll lose that artesian system. You'll have to wait for recharge to fill it back up to repressurize. Yes?
The pressure is coming from the restriction between the...
It's coming from the restriction, and it's coming from the height of the water. That's how a toilet works. You know, the tank holds the water above the bowl. So that when you hit the little handle, the gravity pulls the water down from the higher end, and it has power to move things down the pipe. That's why we have water towers. Water towers store water at a height, and that maintains the pressure in your pressure. But if this gets empty, and that water table drops, you know, that water table starts getting lower. When the water table gets here, well, here it's below the surface. So the water in the well will only flow up to here. And then you'll have to put a pump in.
And it's no longer fancy water.
Exactly. It has these different labels. Well, no, see, then you market it as formerly artesian. Or future artesian water. People
so basically, if you're tapping into it in multiple places, you're relieving the restriction kind of, because it's not as restricted as it was.
Well, it's not so much that it's not restricted, it's that you're using it, you're pulling it out faster than they can get back in, because it's got a limited recharge space. It's got a smaller area where the water can come back in to keep it full.
Okay.
Yeah. So when you have multiple users, you can deplete that artesian property very quickly. Any other questions? You may also hear the word artesian spring. Again, artesian means it comes out of the ground under its own pressure. All springs do that. That's why they're springing out of the ground. So you don't really need the word artesian. Groundwater is a great thing. Not quite 2/3 of the world's population relies on groundwater as their primary source for drinking, agriculture, and industry. There are reasons why. This sounds like a homework question. There are reasons why. Yeah, you've been waiting. Yes, yes. There are reasons why groundwater is usually a better source for drinking water than lakes and streams and surface water. I'll tell you next week. No, I'll tell you. Better be on Tuesday. I'll tell you Thursday next week.
Well, I'm not going to be here.
I'm going to be here. I'll call you. Water. And to illustrate this, I have a little story, so you have to use your imaginations this morning.
I think we're too tired.
Oh, you can do it. It's easy. I'll paint the picture for you.
Okay.
And if you're really good, I got a gross story for you at the end of class. Actually, I got a few. So, number one. Okay, let's assume that because of the big 1913 flood in Dayton, you now live away from the river, up on the top of the hill. Maybe you live up in North Dayton, up North Salem Hill, up North Main Street Hill, up in Old Dayton. Maybe you live south of town, up South 48, up the big hill into Oakwood. Maybe you live west of town, up Germantown, up by the Fractional Institute or the VA Cemetery, up that big hill. Or maybe you live east of town, up the 3rd Street Hill on your way up to Smithville. Maybe you live up at that big hill. So every morning you got to get up extra early and get your bucket, and come down to the river to get your water, and then go back up to the house so you have water for brushing your teeth and washing for your breakfast dishes. And then in the afternoon, you come home from work or school, and you go back down to the river with your buckets, and you fill the buckets, and you bring them home so you have your water for washing for lunch and things like that. And then when you come home at night from work or school, you get your buckets, and you go back down to the river, and you come back with your river water for your nightly washing and your toothbrushing and all that before you go to bed. Now, how many times are you going to make that trip before it gets old? Once, maybe half of once. Okay. Maybe you fill those buckets and realize that a gallon of water weighs 8 1/4 pounds, and you're going back up the hill going, forget this, I'm done. That's why people back in the day had a lot of kids. Because as soon as the kids got old enough to be able to carry the bucket, guess what their job was? The bucket. That gets old fast. It's very inconvenient, time-consuming, and labor-intensive. Now, groundwater tends to be a regional supply. It's more widespread. Forget going to the river 5 times a day. Put a well in your backyard. Then you just walk outside in the morning in your pajamas and just get the bucket and, pump the water and then bring it inside. Or better yet, put a hose on the end of that and put it right into the kitchen and have it come right out of the kitchen faucet. So groundwater tends to be a much more widespread, more regional supply of water, which allows you to be protected against flooding by living on a hill, but yet still have a water source. There's one. There's one. 2. You got your buckets, and I don't know, it's 4 o'clock in the afternoon in August, and it's like 98 degrees with 400% humidity, and you're dragging your buckets down to the river, and it hasn't rained since late April, and you get to the river, and there is no water. You're in drought, the river's dried up. Then what are you going to do? Groundwater. God, you're going to drag the buckets all the way back up the hill empty. So, groundwater is not exposed to the atmosphere. It doesn't experience evaporation like surface water does. And when rivers and streams are in flood, they have too much water, they pump a lot of that water back into the ground system as recharge. They kind of bank it. They make a deposit of water, and that keeps that full. Now, in times of drought, you may have to drill lower to get to the water table, and you may have to have some water restrictions to maintain your water supplies until the rains come back. But groundwater tends to be a lot more reliable, a lot more consistent, a lot more steady supply of water, even in times of drought. Now let's say you go down to the river, and you get closer to the river, and there are all kinds of flashing lights, and police are there, and fire department's there, and hazmat's there, and there are a bunch of ambulances, and the guys in suits with respiratory masks. Step back now, step back. What the hell happened? Who knows? There's been a train derailment, or a tanker truck fell off the overpass, and something has spilled into the river, and the water's purple with orange foam, and there's green fumes coming out of it, and the fish are crawling out screaming on fire. What are you going to do? So, surface water is a lot more open to contamination and experiences pollution a lot more frequently than groundwater. Now, it's not to say that we have no contaminated groundwater, because unfortunately we do, but it tends to be cleaner than most surface supplies. The tiny holes and passages that the groundwater has to flow through give time for heavier, more dense contaminants to sink to the bottom, and lighter materials to float to the top so that it has materials separated. You have time for bacteria. Yes, there are bacteria living down there. You have bacteria that can consume some of your organic contamination and remove that. There's time for interaction with the surrounding rocks and minerals that can have a neutralizing effect on certain chemicals. You have time. So it acts a bit as a filtration system to help reduce and remove a lot of potential contaminants. So groundwater is not always, but it's usually cleaner than most surface water.
So like how we went from going down our swing and buckets to hazmat suits and
Yeah. It can happen. We have just standing here in view, of course the wall wasn't there, you know. In view from here, there are 3 bridges that cross the river, and there are 3 more going that way. So yeah, I can have something falls off of that overpass. So those are our 3 reasons. Groundwater is not without its problems. It is a natural system, and there are problems that occur with natural processes, things that interact in ways that are detrimental. But unfortunately, there are a lot of human activities that also contribute to groundwater problems. Let's look at a few of those. Now, I'm just making a list. They're not in any kind of order or anything. So first one, the lowering of water table and or the reversing of what direction the water in the ground is flowing in. Let's see, we also have saltwater intrusion. So we have the intrusion, the invasion, the incursion. None of those words sound good. We have the invasion of salt water into the fresh water in the aquifer. We also have a situation referred to as groundwater mining, which leads to the sinking or the subsidence of the ground surface. We have pollution. In some cases, pollution can come from natural sources. For example, in portions of Bangladesh, their groundwater runs through volcanic rock. And in that volcanic rock are high concentrations of minerals like realgar and orpiment.
Who?
Yeah, what? Yeah. These guys, you didn't see, you'll not see these minerals in this lab. They are arsenic sulfides. And they have these areas in southern Bangladesh, because of the types of rocks and minerals that are present, their groundwater contains huge quantities of dissolved arsenic. And there are hundreds of thousands of people throughout that region that suffer from severe arsenic poisoning called arsenicosis. They don't have any options. There is no other source of drinking water in the region. And they're not wealthy enough, they're too economically and culturally depressed, you know, they're low in their society, to be able to have the means to get water from somewhere else. So occasionally, rarely, pollution can come from natural sources. But unfortunately, most of it is, you know, because we did it. last but not least, we have the development of karst topography. Now what I'm going to do next is I'm going to circle the ones that are 100% natural. Okay, I'm done. The number 5 here, development of karst topography, and I'll tell you what that is a little later. That is a natural process. We can't do anything about that. It happens. There are things that we do as people that can make that problem worse, okay, but we don't cause it in the first place. We have these other 4 things that are our fault. We don't need to. We'll start with lowering of the water table and or reversing the flow. We'll start with that first. So we have some houses and our water table. These houses are going to have some wells. We'll put in some wells. This is an unconfined system. These wells are going to need pumps to get the water out of the well and into the house. As these pumps operate, they're literally sucking the water to the bottom of the well. That water is flowing, or trying to flow, through the tiny interconnected pore space, through the tiny little spaces in between individual grains of sand, in between the cracks and crevices and other rocks. And what can happen is that you can pump harder than the water can get there. It's kind of like you got one of those really big, thick, like Wendy's Frosties, the really thick shakes, like the way McDonald's shakes used to be. They've gone down. They're gone. You used to be able to hold McDonald's shake upside down. You get that down, all the shakes. They were so awesome. That was just gross. But like I need another McDonald's milkshake. But you got that big frosty milkshake. You got the straw, and the veins are popping out on your forehead, and just before you pass out, you see the edges of the shake starting to curl around the straw. That's what happens with pumping the groundwater. You start drawing the water faster than it can flow to get there, and that will draw that water table down. And the water table will form this big cone-shaped or funnel, like a funnel, big funnel-shaped depression at the bottom of the well. So this goes around in a circle. It's like a funnel. That's your milkshake sucking in around the edges of the straw and on the bottom. That's called a cone of depression. Called a cone of depression, not to be confused with the rock fever of happiness. Called a cone of depression. Now, what this can do is that if you're not monitoring and you're not careful with how many people you have back in the same system, if you're not careful with keeping track and monitoring the aggressiveness of your pumping and how you're getting that water out of there, if you have a user that's got a really deep well, has a higher demand, and he starts pumping this more aggressively, that can really draw that down. And then what's going to happen? Some of these wells, they're going to go dry. That one well can actually draw the water table below the other wells in the area. So they just start sucking air. So you can lower the whole water table in the region. Seriously, they're not, because then they're going to either have to spend hundreds of dollars to get the well deeper, or potentially thousands of dollars to get put on the city system. Yeah. Or just a few, a couple, $20 on a baseball bat to go over here and take care of it. Depends on how you look at it. Yeah, that's why years ago. Then you have all the water left in for it.
And do they use like gauges, everybody's kind of a gauge or something, and tell what's happening or not?
Typically, that's something that would be handled at a county or regional level. And that is why, in many cases, you'll have communities where the county or the state or the city, the regional municipality, whatever level it may be, will come to certain developments and say, look, they've just built another big development down the street from you. You can't all be on wells. This is not going to support that. You're going to have to go to the city system. So that's what they look at. Because once this water table is lowered, then it's just going to keep getting lower and lower and lower, because it's getting lower because you're having too many users pumping too aggressively. The demand is too high, and obviously the demand has become such that recharge alone can't keep that full to meet that demand for everybody. Now, this kind of aggressive pumping can also change the flow of the water. Before, the water was flowing to all of these other wells. Well, now it's just being sucked to that one. So it can actually reverse the direction of how that water is flowing, which can also cause wells to go dry. It is a useful strategy, however, when it comes to dealing with some types of water pollution, because wells can be put in strategically, intentionally to pump, to draw contamination away from an aquifer. So it doesn't flow into it, it flows in a different direction away from it. So it can be used to advantage. Then we got saltwater intrusion. In saltwater intrusion, you're usually going to have an area that's near a coast with an ocean, like Florida or Long Island. When you're near the ocean, you have actually two water tables. You have a freshwater table and below that you have a saltwater table. Saltwater has a higher density than freshwater, so it will always be at the bottom. Pretty much any aquifer, if you go deep enough, you'll run into saltwater. But if you're near an ocean coast, that saltwater just comes in from the ocean. In some parts of Florida, they have less than 5 feet thick of fresh water in their aquifer. You've got to be very, very careful how you control, how you regulate the pumping of that water for usage. When you have the well in here and you start pumping the water out, you're going to form a cone of depression. And that cone will draw that water table down. Well, that pumping draws the freshwater table down. What's it going to do to the saltwater table? It's going to draw it up. If you're not careful, especially on the city system, for example, the city of Dayton has 5 well fields throughout Montgomery County where they pump water. One of the biggest fields is right down there by the Hydro Bowl, off of Route 4 down on Woodman. That's that fenced-in area. That's why it's fenced in. There are about 83 wells there that are pumped, but they're pumped in a specified sequence, so they're not all going at the same time. You got to monitor that, because if you don't regulate, don't do that carefully, the pump on, off, on, off, on, off, on, off, on, off, on, off, off, on, off, off. You're going to get that water table bouncing. Going to depression, gone. Going to depression, gone. Going to depression, gone. Going to depression, you know, on, off. And when you get those water tables bouncing up and down, they can slosh. And when they slosh, you get mixing. When you mix fresh water with salt water, what do you get more of? Fresh water or salt water? Salt water. If I have a glass of water and a glass of salt water, and I pour the salt water into the glass of fresh water, you still can't drink it. It's too salty. Once that's mixed, you can't separate it. You have to wait for rainfall or snow melt to rinse the salt water back down to the bottom and reestablish a layer of fresh water on top, and that can take centuries. Long Island had some of the best drinking water on the planet. In the 1930s, uncontrolled pumping caused saltwater intrusion and ruined the aquifer. The last 40 years or so, they've been trying to rinse the salt water out of the aquifer by pumping reclaimed sewage treatment water back into the aquifer. Now that's water that's been through sewage treatment, and then it's pumped back into the ground to continue and complete its cleaning process naturally. And they're having some success, but it's still a long way out before that's reestablished as a usable aquifer. They're trying to do this because they're losing their money through their teeth. Right now, New York City gets the majority of its water from the Adirondacks. The mountains in northern and central New York, they have big pipes, underground pipes, big aqueducts that funnel snow melt and rainfall down to the city. And they're building new ones all the time. It costs a lot of money. It's very expensive. So if they can reestablish that aquifer, then that saves them a lot of money. But it's going to take a long time. A long time. Much of central and southern Florida has serious issues with saltwater intrusion. They've lost a lot of their fresh water. Most water coming out of the ground is too salty for human consumption. It's way too salty for irrigation. It has to go through processing to remove the salt, either by evaporation or reverse osmosis, and that costs money. Who pays for that? Whoever's paying the water bill at home pays for that. So that's a huge problem. Groundwater mining, that's another huge problem. Look at that. In many areas, if you go underground, you'll find different layers of rock and sediment. Soil for a tree. And then we'll put some clay, and we'll put some sand. Clay. Maybe some sand. That's enough. Some parts of the world, through geologic time, you've had changes in rivers and streams, changes in sea level, changes in glaciers being there and they've gone, changes in the formation of lakes. You know, you get the deposition of sediment changing through time. And it's actually quite common. You get alternating layers of materials. In this case, I've drawn alternating layers of sand and clay. Sand will make sandstone. So as an aquifer, sand is pretty good. The clay, on the other hand, clay becomes shale. Individual particles of clay are little tiny submicroscopic flakes about the shape of a dinner plate. When they settle out of water, they lay flat, and they overlap each other and lock together from these thin, tight layers. Now, anyone that's worked with clay, taken a ceramics class or a pottery class, that clay can be really, really wet and hold a lot of water. But what do you have to do to get the water out of it? You have to put your finished piece in a kiln. You have to bake it in an oven. You have to literally boil the water out of it. It won't flow through and drip out on its own. It won't evaporate out on its own. Clays like shales are aquicludes. They're aquitars. They don't like to let water flow through them vertically. So they'll act as barriers to water. So in this area that I drew on the board, we're going to practice some groundwater mining. Let's look at this first. Think about that. Mining, groundwater mining. If you're going to mine diamonds, you're going to go to where you found diamonds in the rock, and you're going to dig the rock up, and you're going to take all the diamonds out of it, and that's it, right? That's your mining diamonds. Do you have any intentions of ever putting those diamonds back when you're done with it? Oh, hell no. That's kind of like the point. So mining, in the process of mining, you're permanently removing material that you don't have any intentions of replacing later. Groundwater mining, what does that imply? That implies that you're removing the water from the ground without any intentions of putting it back in. Groundwater mining is a situation where the groundwater is being removed much more quickly than it can stay full. Recharge can't keep up with it.
Would that be like for irrigation or something?
Definitely. This is most commonly associated with irrigation in arid climates.
But if it's irrigation, doesn't that put it back?
Well, you would think.
It won't 100%.
Yeah. Well, you have to think hydrologic cycle. The reason you're doing irrigation for crops is because you don't have enough rainfall, you're dry. So most of your irrigation, anywhere from 70 to 85% of the water you're going to use for irrigation will evaporate into the atmosphere. So it evaporates into the atmosphere, okay, well then wind blows it somewhere else and rains somewhere else and they have floods. But it doesn't necessarily get back to you where you took it out. So it gets redistributed. Yeah. So let's see our situation here. Let's pop a well. There we go. We're going to pop a well here in this tank. And we're going to start pumping that water out faster than it can stay full. And that's a sand, not a sandstone, so it's still loose and fluffy. The water in that sand is like the water in a waterbed. It's like the air in an air mattress. The water pressure, the water filling those pore spaces is helping to hold up the materials above it. If you take the water out, you're going to lose that support. That those individual sand grains are going to compact. They're going to pack together. And if that packs together, what's going to happen to the thickness of this layer of sand? It's going to shrink. So now our sand is now only this big. What's going to happen to the layers above it? It's going to sink. So now here's our clay. Here's our soil. Now here's our house. Food tree. We've sunk. That's ground subsidence. The sinking of the ground. It's pore collapse. We've collapsed the pore space. Oh my gosh, you can't do that, because to be an aquifer, you have to have the pore space. You have to have high porosity, high permeability. If you pack the sand closer together, you have less pore space. your porosity will decrease, your permeability will decrease. What will happen to the usefulness of that sand as an aquifer? Oh, shoot. How are we going to fix that? Anybody? 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 We're going to drill to the next one. Now this one's deeper. It's under more weight. So how much faster is this one going to compact being under more weight? A lot faster. Okay. Alright, so now our house is here. And we've lost that sand as a useful aquifer. Oh, shucky darn. How do we fix that? Go to the next one, go to the next one. In the meantime, the land is sinking. That sinking land is going to wreak havoc on all of your building foundations, your roads, your bridge support piers, your underground piping, your communication systems, your telephone poles. Repair. There is a...
Why do they think that would fix it when you open it first?
Well, it doesn't fix it, it just makes it worse. But they need the water for irrigation. So if they run out of water in the one, or they're not getting the supply they need from the one because they compacted too much, they have to have the water, so they go to the next one. Then they go to the next one.
I saw an online article about 3 or 4 weeks ago in California where this guy was drilling for water underground, and they said because of them doing this, I can't remember how many feet, but over so many years, the land has actually lowered.
Oh, yeah.
And now I know why.
Yeah, now you know why.
Yeah.
Yes. Page 717. I do not believe there is a physical geology book on this planet that does not have a picture like this in here. And the goober in the picture is probably a geologist. Or a geologist's grandfather. Hey, Grandpa, go stand by the pole for me. Okay. This picture here of this telephone pole with the old man standing next to it. This is in the San Joaquin Valley in south central California. We've been using that valley for agriculture since the 1920s. Now, central and southern California, as we'll see on Tuesday, is a desert. They get less than 10 inches of precipitation a year. Yesterday it rained, some areas got almost an inch. Just yesterday. Okay? So, desert, less than 10 inches a year. Rain or snow combined. We've been pulling agriculture in this valley using groundwater. That's how you get strawberries in February, right? If you look at the pole, the old man is standing and there's a sign at his feet that says 1977. That's when this picture is taken. Above his head, 1955. That's where he would have been standing, or maybe he was standing because he's old enough to have been alive then, in 1955. There's a sign above that that says 1925. That's where the land was. That's how far it's sunk. This is what, 2015? 40 some years later? Okay, that 1977 sign is probably off the top of the picture. Okay, 2000 is probably where the 1955 sign is now on this picture. Yikes. Once this process happens, you cannot reverse it. You cannot pump water back in there and have the layers all pop back up again. It doesn't work that way. The only thing you can do is to try to keep it from getting worse, which means you either put tight regulations on getting the water out, or you bring in water from an outside source to pump back in to maintain that pressure, maintain the recharge. But then if you can get water from somewhere else, why are you using the groundwater? You think, oh, you go around and around on that one. It's not just water. Places around Galveston, Texas, around the Gulf Coast, have sunk in some areas more than 65 feet. They haven't been pulling water out of there. Offshore Texas, they've been pulling what? Oil and gas. Same problem. Do you want a coastal city that's under the threat of hurricanes to be 60 feet lower? No. That allows storms like hurricanes to come inland much farther and increases coastal flooding. You know, Venice in Italy, with all the canals and everything, oh, they're sinking big time. Primarily because of oil and gas extraction and with increased population, they've also had groundwater mining in the last 50 years. They're scrambling to save whatever historic structures they can. They're fighting a losing battle. Because now global climate change, sea levels rising. Oh, they're take pictures of them now. They won't be around for much longer. Had a good run. So yeah. So that's groundwater subsidence. And then of course there's pollution. Pollution is a huge problem with groundwater. Huge problem. And it can come from many, many sources. It can come from industry, from manufacturing. A lot of pollution comes from mining practices and from agriculture. You get the use of agricultural chemicals, pesticides, herbicides, fertilizers that can get into the groundwater system. You have the use of even organic materials like composted, pig feces or cow manure that are put on fields. That can introduce salmonella or E. coli or coliform bacteria into groundwater. There's the taste treat.
Is that what happened to St. Mary's Lake?
St. Mary's Lake is, talk about fighting a losing battle. They got overrun with cyanobacteria, which is a photosynthetic bacteria that can produce a toxic chemical that kills fish and it can be toxic to humans. They do that because they don't want to be eaten. Okay? What fuels you get a lot of toxic algae as well. And what's fueling that growth is nitrogen and phosphorus, plant fertilizer, coming in off the nearby farm fields.
Yeah, the runoff.
The runoff, yeah. Every now and then you gotta listen, especially in the spring when farmers are getting their fields ready. You gotta watch out for like Union and West Milton, north of town. They still get a lot of their drinking water out of the distilled water. I'd boil that first. But every now and then you get nitrogen alerts. Too much nitrogen in the water interferes with your blood's ability to absorb oxygen, especially in babies and young children. And you get what's called blue baby. Your babies turn blue. Their lips turn blue. Their skin starts looking like skin milk because they're lacking oxygen to get the nitrogen poison. Older people it doesn't bother because your bodies are big enough to deal with it. Yeah.
There's a scuba diving.
Yeah, the scuba gets the nitrogen poisoning. Yeah. So you gotta watch out for that. Pollution also comes from stuff we bury underground pipes. Think of all the gas stations with all their underground tanks of gasoline. You can have an undetectable leak in a gasoline tank underground that can leak literally millions of gallons in a year. Undetected. So you have all kinds of sewage, poorly functioning septic systems. Oh, I got a lot of gross stories about that. Anyway,
how would it be undetected? They know how much gas they purchase. They know how much gas they're pulling.
If you have a pinhole corrosion leak in an underground tank, it can very well be small enough to be below detection by instrumentation. And gasoline is highly volatile, which means it evaporates quickly. And you may notice a loss, but it would not be. It would easily be accountable to evaporation. It would not necessarily be caught as a pinhole leak. Yeah. That's why a lot of times those tanks they undergo regular inspection, and most of them they have of course the newer tanks are much better quality than they used to be. They're double walled and whatnot, and corrosion resistant, yada yada yada. But they have a lifespan of like 25 years. They shouldn't be replaced. But things leak. Oh my gosh, for decades, for almost a century, it was common practice for industry to throw all their leftover unused chemicals in a barrel unlabeled, half the time, who cares? And just bury it out in the field. You know, there are some Superfund sites in this country where you cannot walk on the soil because the soil itself is so badly contaminated with chemicals that it will literally melt your shoes. And when you step, the fumes coming up could kill you. You can't walk there without protective gear. It's that bad. You know, I don't know how familiar you guys are with 55-gallon drums. But you know, you have a big 55-gallon drum, and that's made of steel, and 55 gallons, that's 55 gallons of water. Water weighs about 8 1/4 pounds per gallon. Who wants to do the math here? 50 times 8 would be 400 pounds. So a 55-gallon drum full of water is the weight of the drum, plus at least 500 pounds of water. That's pretty heavy, right? Some chemicals weigh more than that. You can only safely stack those 3, maybe 4 high, because after that the weight of them just collapses, the ones on the bottom. In some Superfund sites where they've been trying to clean up industrial waste from buried barrels, in some places they'll find barrels that are 6 or 7 barrels high, and there's a stack about 12 feet high at the bottom with about 20 collapsed barrels under it. So who knows what was in there that was squeezed out.
Do the chemicals over time ever lose their potency?
Some do. Yes, some do. All will, but it's a matter of time. And you know, it will be self-correcting. The problem is we got to stop putting new things in.
I know a bunch of people that work at Southern Shore Coffee at the Portsmouth nuclear plant down there, and they've been cleaning it up for I don't know how long.
Oh yeah.
But the scheduled completion date is 2057.
Yeah.
I mean, it takes forever
Yeah.
to clean those places up.
Yeah.
Well, it's just so huge. One of the buildings alone is 30 acres.
Yeah.
One building.
Yeah. Well, the EPA has issues and problems because, for example, Fernald also had in southern Ohio had dealt with a lot of deuterium, heavy water, radioactive hydrogen. And they put it all over the place and disposed of it and whatnot. But when they released that to the EPA for cleanup, of course, you know, we're dealing with radioactive materials, you know, potential, you know, terrorists, whatever, bomb threat, whatever. So the government, the EPA's like, okay, well, what's here and what quantities and where did you put it? Oh, we can't tell you that's a matter of national security. Wait, that's going to make it a lot harder for us to figure out where it's at and what it is and how to get it out of here. Can you give us a hint? No, it's a matter of security. We can't tell you where it is. But go find it, get rid of it. Thanks. But we put all kinds of stuff down there. There are some places, I can't think of the name of it, Air Force Base, back in the early 90s in Virginia, where they had so much spilled jet fuel over the decades that you could actually burn the groundwater. That you could, you know, people on wells could turn the faucet on in their kitchen and let the water run, and then hit a cigarette lighter and light it up. That's cool, but it's not good. It's not
The Air Force in Area 51. They
Oh.
buried all their
Oh, that doesn't
chemical
exist.
stuff out in a big thing and burn it.
Burn it, yeah.
And people's skin was falling off that weren't there.
Yeah.
And so they went to court, and the court goes, there isn't.
There's
none. You work at this place that doesn't exist. So
I mean, the place that doesn't exist is they moved to Colorado. Anyway, so pollution, it comes from everywhere. And the problem with it in groundwater is that you can't see it. You know, if something happened, that river down the street, you would come to school or you would go outside after class, and the first thing that you do is go, I got into the river. You know, you go down to the river and it's foaming and it's bubbling and there are dead fish everywhere. You would know there's a problem. You're not going to go walking out here in the grass in front of Building 10 and go, oh, this groundwater is gross. There's got to be something in it. You don't know. The only way you know there's something in there is if you drill a well, and you find it. But you could drill that well, you could put that hole in the ground 4 feet to the left and miss it. So that groundwater, that pollution gets into the groundwater, it can be there for a very long time before anyone finds it, And during that time, it's increasing in concentration and it's increasing in area, spreading out. The only access is through a well. So when it comes time to clean it up, that's your only access, is to drill a hole and try to get it out in the hole. Drilling a hole can cost hundreds to thousands of dollars. Groundwater pollution cleanup usually requires specialized techniques, specialized equipment, and specially trained personnel that know what they're doing. And whenever you have to put the word special in front of something, what does that mean cost-wise? Very expensive. The best strategy against groundwater pollution is to take measures to try to not let it get in there in the first place. That's the best hope you have.
So we're screwed ultimately.
Well, we're getting better. We're getting better. We got to learn. This is all coming from back in the day when we didn't really understand that everything's connected. Didn't really understand it's a hydrologic cycle. That, the river's connected to the dirt's connected to the groundwater's connected to this, that's connected to the atmosphere, it's connected to this. It all flows one into the other. You can't just bury something and forget about it. It's going to show up somewhere else. And nothing's in isolation. So it's been about 50 years of kind of backpedaling to fix those past mistakes and to educate industry and bring in regulation and whatnot. It's a slow process. So do you want to hear about karst topography or do you want to hear a gross story?
Karst topography.
Gross story.
Gross story? Gross story? Okay. You sure you want the gross story?
Yeah.
Okay. So my dad, of course, he grew up in the Depression, 1920s, 1930s. And he lived in a house on Lake Winnipesaukee in New Hampshire. And he had this 1920s, 1930s. His house had a bathroom. That was a big thing back then. And you go into the bathroom, and you lift the toilet seat, and there was the hole, and through the hole you could see the lake. That was the bathroom for the people living on the lake. Now, in the wintertime, his dad and his older brother would take the horses and the saws, and they would go out on the lake to harvest the blocks of ice from the summer ice house. So you would have your ice blocks, to put in your ice box at home, so it'd be dripping all over your food and it'd keep it cold.
I'll give you one.
Is that gross or what?
There's a river that runs between
Yeah.
the naval base in Subic Bay in the Philippines and goes to the town.
Yeah.
It goes right, there's a little bridge you go over. Well, there's a word for that river that starts with an S and ends with a T, and you can put the letters in between.
Yeah.
They call it. Well, there's a little tiny boat, skinny boat,
Uh-huh.
with a little pistol and a girl in a wedding dress sitting up with a basket, and when the guys go by, they'll throw a peso to the
Yeah.
guy. In the water, hang on to the side of the boat, is a little kid.
Oh,
And
boy.
when the truck sailors come through and really don't want to hit the basket, they throw it to the side, the little kid dives down to get it home.
Oh, gross.
1 peso is 1/22 of a dollar.
Yeah.
So that's what we're doing.
Yeah.
And so, yeah, it's pretty gross.
Pretty gross, yeah.
Because all there, they don't have anything out there, sewage just goes wherever.
Oh, yeah, yeah, they
There's
don't have,
no,
they don't have the,
there's
they don't
nothing.
have the money. They don't have the money, yeah. Gross, I am so glad the mom is. I got another story for you. You want to hear another one? Have you heard of the 6 degrees of Kevin Bacon? You heard of that, where, everyone's within 6 degrees of Kevin Bacon? Is there anyone in here that's within 6 degrees of Kevin Bacon? Would you like to be within 6 degrees of Kevin Bacon? My sister's best friend, it's going to be like my cousin and sister's brother's college roommate. Okay. My sister's best friend's son went to Bowling Green University in Ohio, and that's where Kevin Bacon's daughter went to school. And one day, Kevin Bacon was walking around on campus and sat down with her son and some of his friends, and they talked for 2 hours. So you now are within 6 degrees of Kevin Bacon, because you know me, I know my sister has a friend, her friend's son met Kevin Bacon. Within 5 degrees of Kevin Bacon. Isn't that amazing? Yeah, it's true. It's creepy, but it's true. It's true.
What about Kevin Costner? We could do him.
Oh, it's not safe.
I love him.
Any questions? My legs killing me with this weather. I can't stand it anymore. So that's it for me. I'm calling it today.